Yet again, teacher Carlos Plain of Durham School states, "Totally, I went through my entire time on Earth empowering and expressing a theory of the universe. Additionally, finally, the hypothesis is being tested. I welcome that since that is the way we push ahead, that is how we gain ground in science." The James Webb Space Telescope is upsetting an uncommon measure of what has been seen as truth in cosmology. For the new year, another ultra-deep picture shows that we have serious goofs in cosmology. The telescope, which was supposed to show us the essential stars of the universe, is changing into an enemy of the past perspective and may present to us a thoroughly astounding science. Not all experts are grieving in dread at the new realities. Other well-informed specialists invite the advancements since it has, for a long time, been clear that something was the matter with our old theory. The deviation in the assessment of the progression speed of the universe alone should have shaken specialists' perception at last. Previously, however, bringing all that into account, they complied with old theories. The galactic microwave background radiation, CMB, considered the most settled light known to mankind, was made something like 380,000 years after the Big Bang, exactly when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Researchers call this process reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were dealing with another type of radio-receiving antenna technology. This discovery was for a surprisingly long time seen as possibly the strongest piece of evidence for the theory of the old Big Bang, earning Penzias and Wilson a Nobel Prize and an obvious place throughout the entire history of astronomy. The CMB in all probability offers a viewpoint on the early universe, with little temperature differences giving fundamental data about the conditions not long after the Big Bang. Physicists included the CMB as a solid scratching of the crucial assessments of the material universe to check the expansion speed of the universe, among other things. The cosmologist Edwin Hubble had previously settled this in the late 1920s, finding that distant systems retreat from us and that their speed is proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have the high-level surveying methodologies available many years later when the CMB was discovered, which led to a recalculated expansion rate. These were considerably lower than Hubble's original figure. Later, experts recalculated the rate using type Ia supernovae as standard candles, giving stable light that could be used as a solid measuring point. The estimates within the CMB yielded an expansion speed of around 67 km per second per megaparsec, while gauges using vast explosions yielded around 74 km per second per megaparsec. What does this disparity in determining the expansion speed of the universe really tell us? Did you realize that this goof has been known since the 1990s? Since that point, inspectors have known, or at least felt, that something may be wrong with the evaluation of the CMB, the appraisal techniques, or the possibility of the universe's expansion. The anomaly between the observed and expected values of the expansion rate is referred to in science as the SAA strain or Hubble strain. The ramifications of this strain are tremendous, suggesting that fundamental bits of how we understand the universe may be deficient. For a long time, specialists were frustrated. Since the James Webb Space Telescope went into action, it has furnished experts with stunning data that may now uncover information on the issue of the expansion speed of the universe. With systems so old and mature that their development should have started theoretically before the Big Bang, upsetting old cosmology, scientists no longer discuss mistakes or appraisal differences. They discuss the emergency in current astronomy. Not only could the expansion rate be inaccurate, but the whole concept of evolution, or the Big Bang itself, is being raised. Pictures from the telescope provide evidence of a universe completely unexpected from what we have long thought. The SAA pressure was the chief reprimand to specialists who still have faith in old theory. Now they manage an issue. Do we truly understand the universe? Different researchers stand on the remains of their once brilliant source of both discovery and torment, examining space with fear and wrestling with what they find. Considering the emergency in science, we must ask ourselves, what do we truly know about the universe? To answer this, we need to grasp how science works. Speculative experts utilize a complicated set of mathematical models, wary data, and keen reasoning to move conclusions from the general to the specific. Their understanding comes from a blend of discernment, credits, significant outcomes, and speculative evaluations. The term theory alone shows that these are developments and contemplations, not outright pieces of information. The key critical data we have are the photographs telescopes provide, the the sound waves and radiation gathered with radio telescopes, and the latest information from neutrino surveying systems or gravitational wave markers. With the James Webb Space Telescope, we now have an instrument that can split the light into individual frequencies and analyze it in remarkable ways. Webb can show us the fundamental pieces of galaxies in the early universe billions of years ago, how much mass they contained, and the number of stars present. It can also trace the shape and course of a galaxy's development. Webb, however, has limitations. For example, it can't always determine with certainty whether we are seeing galaxies or, on the other hand, black holes with gigantic gravitational forces that emit as brightly as a galaxy. We must face the reality that our science has long accepted too many possibilities as facts while dismissing alternative explanations. Research has long been certain about its accuracy. The latest discoveries from the James Webb Space Telescope are fundamental hints to replace speculations with new insights, as has happened many times in science. Experts are eagerly expecting the new discoveries, which are unexpectedly shocking, and various specialists are striving to develop new explanations. The new discoveries shake the underpinnings of our current science, disturbing many specialists. The current models of real-world science are still largely based on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our understanding of the reality of this world and the universe for a long time. Newton's principles grasp the motion of things under normal conditions and work particularly well on Earth. However, in space, his theories required advancement, which was largely done by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, changed how we interpret reality, showing that realities are relative to each other and depend on the observer's motion. His general theory of relativity, published in 1915, expanded this idea with mathematical descriptions of gravitational characteristics based on the curvature of spacetime by masses like stars or galaxies. Einstein's theories and considerations were significant in many areas. However, he too recognized their limitations. He knew his theory could never fully describe the universe and yearned to see a unified theory, which he never achieved. No other expert has reached this stage either. Wouldn't it be fascinating to know where it lies? Michio Kaku, a prominent astrophysicist from the USA, said in an interview that resolving this issue would certainly win a Nobel Prize. Could we investigate whether the experts might have missed possible misinterpretations, or whether our telescopes are to blame? Dark matter and dark energy are at the top of the suspect list for the key reasons behind the cosmological emergency. Our evolving models of the universe combine ideas that dark matter and dark energy make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They likely exist in some form or shape, requiring alternative explanations for the universe's development and the dynamics of galaxies. On the other hand, they could have properties we don't yet understand. One idea is that the true properties of dark matter and dark energy have changed over time, possibly showing some form of evolution. Gravity is another hypothesis to be tested. This force, which causes attraction through mass or curvature in spacetime, has not yet been fully explained. The concepts of spacetime curvature, which stem from Einstein and have been traditionally supported, may require revisiting. We can't dismiss the possibility that gravity has unexpected properties or that another force is responsible for the gravitational attraction between objects over time. A few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been a journey defined by our constant quest for understanding and discovery. From ancient human civilizations observing the stars to current space telescopes exploring the depths of the universe, each step toward advancement and theory has uncovered new mysteries while challenging established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, remains a beacon of our scientific progress, promising to change how we interpret the universe's origins and evolution. Launched with remarkable capabilities, JWST represents a leap forward in observational space science, designed to look deeper into the universe than ever before with exceptional precision. With the James Webb Space Telescope, JWST, now operational, scientists are poised to make new discoveries that could reshape our understanding of the universe. The telescope is designed to peer deeper into space and time than ever before, revealing details of distant galaxies, stars, and other celestial bodies that were previously obscured by the limitations of earlier technologies. As it continues to send back data, the JWST will help us probe the early universe, possibly shedding light on the formation of the first galaxies and stars, and providing evidence that could lead to a new chapter in cosmology. The significance of JWST lies not just in its technical capabilities, but in the potential it holds for answering some of the most profound questions in science. What is the true nature of dark matter and dark energy? How did the first galaxies form, and what were the conditions that led to the birth of stars and planetary systems? These are questions that could be answered by analyzing the data that the JWST provides. But with these new insights comes the realization that we may have to rethink many of our current scientific assumptions, theories, and models. Scientists have long relied on a variety of tools and methods to study the universe, but JWST represents a new frontier in observational space science. Its ability to capture infrared light, for example, allows it to see through the dust clouds that obscure many distant objects, giving us a clearer view of the universe's past. The telescope is also capable of studying exoplanets and their atmospheres in unprecedented detail, potentially identifying signs of habitability or even life beyond Earth. However, as with all great scientific endeavors, the discoveries made by the JWST will likely raise as many questions as they answer. The more we learn about the universe, the more we realize how little we truly know. What may seem like a breakthrough today could be upended tomorrow by a new discovery, leading us to reconsider everything we thought we understood. This is the nature of science, a continuous process of refining our understanding, challenging our assumptions, and seeking ever deeper truths. As researchers continue to analyze the data sent back by the JWST, we are at the cusp of a new era in cosmology and astrophysics. The telescope's discoveries are likely to influence not only our understanding of the universe but also our place within it. With every new piece of information, we draw closer to understanding the origins and future of our cosmos. The path forward may be full of uncertainties and challenges, but it is through these very challenges that we continue to push the boundaries of human knowledge and explore the mysteries of the universe. Ultimately, the James Webb Space Telescope may prove to be one of the most significant scientific achievements of our time. Its discoveries will shape the future of cosmology, providing us with insights that will likely inspire new generations of scientists to explore the cosmos in ways we can only imagine today. As we continue to look to the stars, the JWST offers a glimpse into a future where we can finally answer some of the most profound questions about the universe's past, present, and future. As the James Webb Space Telescope, JWST, continues to push the limits of our understanding, its discoveries will likely have far-reaching implications beyond the realm of astronomy and cosmology. The data it collects has the potential to influence various scientific fields, including physics, chemistry, and even biology. As we uncover more about the origins of the universe, the birth of galaxies, and the formation of stars and planets, we may also gain new insights into the fundamental forces and processes that govern the universe. For instance, by studying the early universe, JWST may help clarify the mysterious nature of dark matter and dark energy, two of the biggest enigmas in modern physics. Dark matter, which is believed to make up a significant portion of the universe's mass, and dark energy, which is thought to drive the accelerated expansion of the universe, remain largely undetectable. Understanding their properties could open up entirely new fields of study and lead to a deeper understanding of the universe's structure and behavior. Moreover, the search for life beyond Earth, a long-standing scientific quest, could receive a significant boost from the JWST. By studying the atmospheres of exoplanets, the telescope might detect signs of habitability, such as water vapor, oxygen, or methane, which could suggest the presence of life. While the discovery of extraterrestrial life remains elusive, the tools provided by JWST could bring us closer to answering one of humanity's most profound questions: are we alone in the universe? The telescope's ability to explore distant galaxies and look back in time to when the first stars and galaxies formed may also change our understanding of the universe's evolution. This could lead to a reevaluation of cosmological models and theories that have stood for decades. For example, if the JWST reveals new details about the formation of the first galaxies, it could challenge existing ideas about the timeline of the universe and its growth. As researchers and scientists delve deeper into the data sent back by the JWST, they will undoubtedly encounter new mysteries and challenges that will require innovative thinking and collaboration. The answers they find may raise even more questions, pushing the boundaries of what we know and deepening our understanding of the cosmos. In this way, the JWST not only promises to answer some of the most profound questions in science, but also to create new avenues for exploration and discovery. The telescope's findings will also likely inspire future generations of scientists, engineers, and explorers, continuing the legacy of scientific curiosity that has driven humanity to seek answers about the nature of the universe. Just as the Hubble Space Telescope and other observatories have opened our eyes to the vastness and complexity of the cosmos, the JWST offers a glimpse into a new era of space exploration, one that promises to expand our knowledge and challenge our perception of the universe in ways we have yet to imagine. In the years to come, as JWST uncovers new truths and reveals the hidden depths of the cosmos, we may find ourselves on the cusp of a new understanding of the universe and our place within it. The journey is just beginning, and the potential discoveries are limitless. The quest for knowledge is an ongoing adventure, one that will continue to shape the course of human history and inspire generations to come. With the James Webb Space Telescope, we have taken a giant leap forward, but the journey through the cosmos is far from over.